Welcome everyone back to the second part of Intuition for Maxwell. Good to have you back, Sam.
Well, always nice to be here.
And what we're going to do is start with the lossless transmission line equations. But before we do that, let's remind ourselves of the model. Here are the two plates or wires, conductors of the transmission line, voltage from this plate to this one, and the current down the line. And normally we're going to think down the line is in the Z direction, and between the plates is in the X direction. Now remember, when we go to fields, the voltage is going to be replaced by EX. So there's the electric field in the X direction. And we did the analysis in the previous intuition video, the magnetic field, black, in the plane, perpendicular to the plane of the red and green pen, that's HY. So I is going to be replaced by HY. Now let's look at our equations for the transmission line. Here they are, lossless, dV dz is minus L di dt, and the I dz is minus C dV dt. What's important are the units. L, inductance per length, henries per meter. C, capacitance per length, farads per meter. V in volts, I in amps. Sam, can you put these now in terms of field equations rather than transmission line setting?
I'm up for the challenge. Let's see, we start with replacing V with EX and I with HY.
Yep.
dEX, dZ, and we replace L by mu naught, dHy, dZ. Did I get this right?
No,
dt.
Typo there. No, it's a T.
Typo, righto.
Typo, ripo, put in the T. So mu naught means what kind of material?
Vacuum.
Vacuum, right. Hey, isn't that weird? A vacuum can actually have a permeability. Weird, huh?
What goes to it?
Well, this is a great problem that gave Nobel Prizes, and people had trouble at the beginning of the 20th century figuring out why a vacuum should have permeability. And give us the next equation, Sam.
Well, also up for the challenge. Hy, dz is negative epsilon naught, dEx, dt.
So what about this guy? What's that?
Isn't it the permittivity constant?
Yeah, and its units are?
Farads per meter?
Farads per meter. Hey, a vacuum also has permittivity per length. Weird. I thought a vacuum didn't have anything in it.
Yeah, well, I thought that's what the word means.
Well, that's so bizarre. I just can't figure it out. Neither could the great Nobel laureates of the 20th century transition. Anyway, look at this. We now have the Maxwell equations in one dimension. We want to show you something else with what we've been able to do intuitively. Let's get the plates back here and look at the field lines, where the fields are going. So EX is going this way. It's going up and down. H is going in the Y direction. So what happens in time is you get vibrations here. So the wave is vibrating in this direction, and the H wave is vibrating perpendicular. So the two vibrations of E and H, in this case they are in phase, and they're vibrating orthogonally with respect to one another, perpendicularly. H vibrating along the y-axis and EX vibrating along the x-axis. And so without any fancy equations, we've got the fundamentals of wave propagation in 1D using Maxwell. Now, what happens is the vibrations are basically restricted at any point to the plane containing the magnetic and electric fields. So this plane is perpendicular to the direction of energy flow along the green, along the direction the wave is traveling. And for that reason, it's called TEM propagation. So you can check a good exercise, exactly get the vibration meaning of TEM from your book. it's a characteristic of one-dimensional propagation. When we get waveguides, we'll have more things, waves bouncing around, and then that's no longer true. You have anything else we can add, Sam, to this?
I don't know, you tell me.
Well, I think we've got to remember that when we solve these equations, our solutions are still going to be f of z minus vt in one dimension. Now, before, v was 1 over root LC. What do you think it is in this case? That's an exercise for the u to figure out what the velocity should be. By the way, the other thing is we've got to do better. We're going to rewrite this in the form of alpha t minus z over v. And we're going to see how we can extend this to multi-dimensions. We've just got the one-dimensional case here, and that's a subject for future videos.
Wow, you're signing them up for a huge challenge.
Oh yeah, optics on the move, coming up in about a few weeks.